on solute concentrations on either side of the membrane. Okay? And again, this one's tricky. It is tricky, right? So, movement of water through the semi-permeable membrane is going to move from low solute concentration to high solute concentration. You can think about it though, high water to low water. Because what the water is trying to do is trying to dilute the higher concentration solid. Okay? So, the thing that comes into play here is what we call tonicity. Tonicity is defined as the ability of a solution to cause a cell to either gain water or lose water. And tonicity is straight up due to the presence of non-penetrating solutes. So that means that they're going to be trapped wherever they are and they can't move across the membrane to equilibrate. Okay, they can't equilibrate. Now on here, we'll start on this side right here, we're showing the three examples, and we're going to be trying to do this in the laboratory today. So, you know, dialysis, you've probably heard about this maybe because they do kidney dialysis and so on to filter the blood. We've got up there a dialysis bag, which represents our cell. And then we have three different environments, which represents the environments the cells are actually located in. We have one that's called hypotonic, one that's called hypertonic, one that's called isotonic in terms of our three conditions. So we start over here with a hypotonic example. And so with our cell at the top, represented by that bag, we're going to have 98% water, 2% solute, has to add up to 100%. So we're going to stick that cell now into an environment that has 100% water. That means 0% solute, okay? And this condition is characterized as being hypotonic. And the thing you've got to kind of think about here and notice is that our prefix kind of indicates the solute relationship we're trying to think about. And this hypotonic, hypertonic, isotonic always refers to what's outside the cell, not what's in the cell. So hypo means less than, solute-wise. So we have 2% solute inside of the cell, but we have 0% solute outside. So the solute is less out here than it is in here. And with a hypotonic sort of environment, because water always moves from lower solute to high, or high water to low, that's the best way to think about it. Even though 98% isn't too much lower than 100, it's still lower. So that means that the direction of water movement is going to be from the environment into the cell. So we move, again, now water into the cell. And the effect then is going to be that the cell is going to get larger. Because as water moves into here, this is going to clump up. All right? And again, hypo means fewer solutes out here than in here. We could change this to say 98 to 2% in the cell still would make this 99 and 1%. 1% still would make it hypo because it's less than 2, right? Okay. All right, second condition. Same cell. 98% and 2%, but this time solutes are going to be higher in the environment. Okay? So you can see up there it says 90% water, and now we got 10% solute. Right? So this condition is hypertonic. Hyper means more than. Okay? And again, we're always thinking about what the condition is here relative to here, not what's in here relative to out here. Okay? So because we have more solute on the outside, less solute in the cell, but at the same time, it's easier to recognize there's more water here than there is here. Water's gonna go out of the cell, okay? The water goes out, and what happens is that the cell itself does get smaller, okay? All right, does everybody see that? Sure. Okay, last one now. Everything's equal. Okay, this is easy here. So you've got again 98% here, 2% right there. Out here, same thing. 98%, 2%. Okay? So because there is no difference, that means in the end there's no net water movement one way or the other. We still get water moving that direction, but for every amount that moves that way, the same amount moves to the outside. Okay? And in this case right here, there's no shape change. So the cell shape, size remains the same. This one is isotonic. Okay? And again, iso means same. So this is the idea of movement of water across the semi-permeable membrane. The important thing here to recognize again is iso, hyper, hypo refer to the solutes out here, outside the cell. And then the other thing to remember is that these solutes, like right here, 10%, they can't move into the cell. They're trapped. They're non-penetrating. So that maintains this solute concentration. So anyway, on my blood cell pictures right here, you can see that with the water moving into the cell, red blood cells actually get real, kind of blow up like a balloon. They will actually break completely apart with 100% water. When you have the hypertonic condition and the fluid moves out of the red blood cell, they get a little pointy little crenulated kind of deals on them, as you can see right there. And then when it's isotonic, water's moving both ways, so you end up with what is a normal looking red blood cell, which is kind of looks like an inner tube with a little what membrane in the center, right? Kind of a donut with a membrane, jelly donut, right? So anyway, that's the idea of the water movement. And again, it's always important to remember, and I say this 1,000 times, we're talking about, again, outside of the cell. Cell's the same in all three examples. 98 and 2, right? So what you want to think about, what's going on outside the cell to determine whether it's hypo, hyper, or iso, okay? And again, we can vary these all over the place, you know, do different numbers. So, you know, I could make this one right here, it's 98 and 2 right there, but I could also make this 80 and 20. Or you can make this a 95 and 5. Still is hyper. And on my little extra credit deal, I'm going to ask you to kind of evaluate an example of this. And so again, the most important thing on this, and one thing that a lot of people feel like they don't have time to do, draw the stupid picture. Draw the stupid picture. Draw the little box, put your little round circle in it, write the cell concentration inside of there, and then whatever you've got for your outside environment, write that on the picture. That's how you see the relationship. 1 out of 10 can do it here. 9 out of 10 will mess part of it up, and it won't take you any time. On the test, there will be one of these on the test. Draw the picture. Okay, what the conditions are. Draw the picture so you can see the relationship. Then you can tell hypotonic, hypertonic, isotonic. You can tell, is the water moving what? Into the cell, or is it moving out of the cell, or is it kind of moving both ways and there's no change? Okay. So anyhow, a little suggestion right here. Makes it a lot simpler. All right, so again, you're always thinking about the solute condition outside the cell. Hypo is less than, hyper is more than, iso is the same. You need to remember that these solutes right here cannot go into the cell. They're non-penetrating. You know, that's what kind of establishes the condition. All right? And then the water always moves low solute to high. It's easier to think, though, high water to low. So from whatever the higher water value is, it'll move toward the area of a lower water value. Right, here's another one. In fact, we didn't use that one. In a lab today, we're going to use sheep blood to try to demonstrate hypotonic, isotonic, and hypertonic conditions. It's going to be a super fast deal. I'm probably going to have like a group of 3 do 3 tubes. You're going to put a little bit of sheep blood at the bottom of the test tube, and then you're going to put a comparable amount of our 3 different solutions. We will have an isotonic solution, which is 0.9 saline, which is like hospital kind of isotonic IV bag kind of stuff. And you will put that into the tube with the sheep's blood, and you will see that it'll still look exactly like the sheep's blood itself. You will put 100% water into the second tube, and what's going to happen is all that water is going to rush into the red cells, and they're going to break like an overinflated balloon, just like that. And that solution will turn super red transparent, look like, you know, what big red is, right? Mm-hmm. That's the way it'll look, right? And then the hypertonic, we're going to use sucrose, 40%. That's going to suck water out of the cells. This is the hardest one to relate to, but you're going to have to look to see that it's got a kind of a cloudiness that's in between isotonic and clarity. So anyway, that's how we're going to demonstrate osmosis in the laboratory. And this is just illustrating here that, again, if you've got isotonic solutions, cells stay the same. If you put them in 100% water, a red cell will take on so much water that within 1 second they'll all just break completely apart. All the cell parts will lay at the bottom, and you'll just be left with the red fluid with hemoglobin, transparent. And if you suck all the water out of them, they'll get all tiny. A little more light passes through them, so you'll see a little less of a cloudiness than you do with the isotonic. So anyway, we'll see how that goes today. All right, so anybody got a thought?